All right. How's everyone doing today? Y'all all right? Tired? I'm tired too. Um, these are the homework problems that I asked you to do. Any questions on the homework? The fourth one? Four would probably be the hardest one. Let me work through number four. Was that it? Was that four? Okay. All right. So what is the first step? Okay, so the first step, we're going to determine if it opens up or down. Here it opens up, right? Why does it open up? A is 3. 3 is a positive number. So what I'm looking at there is the 3 in front, right? Okay, so I know that this parabola opens up. So it should look something like this. What's the next step? Vertex. So I just need to identify H and K. So H is the opposite of what you see inside the parentheses. So if you see a -2, that means that your H is actually +2. And then your, okay. Oh, okay. I asked if that was the right thing, and people said it was okay. Okay, well, hold on. X minus, it's 3 in here?
Do you even switch it if like everything's positive? Do you still switch the signs?
You mean if that was a +3 instead, you would make it a -3?
You still make it.
Yep. You always switch whatever's there. So the vertex is +3 then? That okay, everyone? Okay, what's your K? -6. Any questions on that part? Okay. All right, the next thing is what? Just a real quick sketch of what we've got here. Why are we doing a quick sketch? What's the advantage of that? Yeah, see if you even have any x-intercepts. So here's a real quick sketch. I'm going to go to the right 3, down 6. Here's my vertex, and my parabola from here must open up, which means I will have 2 x-intercepts, right? So we need to find them. Set the entire function equal to 0. That's how we find x-intercepts, right? So I'm going to take the 3, x minus 3 squared minus 6, set it equal to 0, and then I'm going to get my calculator. All right, so I told you you'd need a calculator, right? Okay, so what you're going to do first, I said whenever we have the standard form, right, you'll move the number over, the number that's by itself. In this case, it's the K. Move the K over, so add 6. That will leave you with a 3 times x minus 3 quantity squared equals 6. Then get rid of the 3 out front. Divide by 3. X minus 3 squared equals 2. And then at this point, what do? Square root property. So square root both sides. And always have to do plus or minus on the right side, correct? On the left side, x minus 3 squared. Right side was the 2. Now, by design, the left side should just get you what was underneath that square root. Right? And then what is the square root of 2? So this is where you'd use your calculator, 1.414. The question will be how many decimals do you go, right? On the test, 1, 2, it's fine. I'm not going to be real critical. Because the idea is that we have to plot that point, right? Nobody's going to be able to plot 1.4141. You're only going to get like 1.1 maybe. How accurate are we really going to be with a graph? So I'm going to say plus or minus 1.4, I'll go 1, okay? Now what we do is we're trying to get x by itself, so we're going to add 3 to both sides. So I'm going to have x, then negative, or plus or minus 1.414, and I'm adding 3 to that. Doesn't matter if you put it in the front or back. So I'll put it this way. You could have written this, 3 plus or minus 1.41. Either way. Yeah. Just don't come in there and add 3 to 1.41 right now and make it 4.41 and then say positive and negative, because that's not what it is. You have to actually do 1.41 plus 3, and then you have to do negative 1.41 plus 3. So two different things happen here. I'm going to write it the way I normally write it over here. Plus or minus 1.41 plus 3, and then the way I did it in class last time, I had like 2 little arrows like this. And I said one of them is when I do the plus, one of them is when I do the minus. So if I treat it as a positive 1.41, I get 4.41, right? And if I subtract, right, negative 1.41, add 3, what do you get? What is it? 1.59. So these are my 2 x-intercepts. Questions on that? Can y'all see the board okay? I have the other light on. Is this all right? Anyone have a problem with the screen? Okay, what is our next step? That was just step 3. So I'll put step 4 over here. The y-intercept. How do we find y-intercepts? Yep, plug 0 into the function. That means I'm going to have a 3. I'm going to have 0. What was it? Take away 3? Squared, and then it was minus 6. So do what's in the parentheses first. 0 take away 3 is negative 3. Square it, and you get 9. 3 times 9 is 27. 21. So you have a y-intercept of 21. What's the 5th step? Graph it. Okay? So I'm going to go to a new page. I'm going to get all fancy on you now. Now, you don't have to use graph paper, right? If you want to, you can. So where do I start? With whatever that was, yeah. Where should I start? Vertex 3, negative 6. So I'm going to go to the right 3, 1, 2, 3. I'm going to mark that point 3. I'm going to go down 6, 1, 2, 3, 4, 5, 6, negative 6. I will put my vertex there. So when I'm looking at your graphs, I want to be able to look at your graph and know what that point is. Like, you can tell what that point is from what I did, right? If I didn't put the 3 and the negative 6 there, it might be difficult for you to determine that, especially if it's not on graph paper. So I want you to at least let me know where that point is. The next point that we found, or the next points that we found, which were what? 4.59. So 3, this is getting kind of tough. 3's right there. 4's the next one, right? So 4.59. I thought there was a 4 point. 4.4. Okay. So 4.4, it's going to be kind of tough to get in here. I'm just going to put the dot right there. It's almost halfway, right? Now you don't have to label that, but you could. You could just draw a little, 4.41, and that way I know where it is. The better your graph is, the easier it is for me to grade. The easier it is for me to grade, the less points get taken off. Does that make sense? All right, what's next? 1.59. So that's going to be about right here, a little bit past 1. I'll go ahead and label that one also, 1.59. And then I have a y-intercept, right? But that y-intercept was way up at what, 21? I don't even know if I'll be able to fit it on here. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. Hold on. 15. It's going to be off the graph. Now, here's where we run into an issue. If I can't fit it on here, I have to rethink the whole thing. I have to go back through and possibly redraw the whole thing if I want everything to look scaled appropriately. Now, you said, why don't we just count those as 2s? You can count each tick, you know what I mean by tick? Each tick mark, you can count it as 2, but that means the ones going down have to be 2 also, which means I'd have to change where that -6 is. That -6 would actually, like if I'm counting those ticks up and down as 2s now, that -6 would actually be a what? It would be a -12, wouldn't it? So I'm just real quick on the fly going to change this. Watch. I'm going to count each tick up and down as a 2. So I erased the -6. I actually need to go down 2, 4, 6. This is now -6, which puts my vertex here. Do you all understand what I did? It's called changing your scale. Yes? They do not. Nope, that was going to be my next point. Whenever you scale, this is called scaling your axes. If you change your scale, whatever's in the y direction, every tick has to be the same. So if it's 2, it's got to be 2 the whole y-axis. But your x's don't have to be 2. Your x's could be 1s. Your x's could be 10s. Your y's could count by hundreds. It doesn't matter. Just whatever, each axis by itself has to be the same. Y'all see how I did that? Now I can count by 2 up, and I'll go what? 2, 4, 6, 8, 10, 12, 14, 16, 18. There's 20 right there. I'm at 21, so right in between there. Probably a little better to see it that way. And then you draw your U, right? We talked last class about this imaginary line. Imaginary is not part of your graph, right? It's this line that goes down the center that we call the axis of symmetry. And that's where we have our mirror image. So I will draw the left side of this and make sure it looks like a U, not a V. Come up through here. Oh man, I just blew it. That's all right. And I just try and get it to be the same thing over here like that, right? No, that's not what I want. Oh, whoa. That was the computer. That had nothing to do with me. Yeah. You get the idea. So when I'm grading these, what I'm looking for, the first thing when I look at, when I'm grading a problem like this on a test, the first thing I do is I look at the graph. If the graph looks good, then I proceed on to your work, okay, where you go and you show me the steps. But I need to see the steps. So if your graph is wrong, you can still get credit on the problem as long as your steps make sense. All right? What are some things you should, I guess, pay attention to? Let's say that you're doing a problem, right? Let's just say you have a problem, and you get to the point where you have a graph, and let's say you have x-intercepts and you find out that they're here. Why does it keep doing that? And let's say that you have your vertex is, let's say, here. What should you be thinking? You did something wrong, okay? Because your axis of symmetry is down the center of the vertex, and there's no way you're going to be able to draw this thing to go through both unless you do something weird like this, which people will do. People always laugh when I do that, and then someone will do that on the test. They'll They'll give me a parabola like that. Okay? Your axis of symmetry splits your parabola in half. Your x-intercept should be equally spaced on both sides of that axis of symmetry. So if that happened, you go back, double check things. The most common mistake is the signs on the x-intercepts. That plus or minus, people will somehow flip it. So instead of getting, let's say, I don't know, well, you know what I'm saying. They'll just mess up those signs. So instead of, let's say, having 2 and 4 as x-intercepts, they'll have -2 and -4 or something. So that's usually the first place you should go look if you've got issues. Okay, any questions? Okay, we're going to move on because all we did last time was graphed quadratic functions in standard form. And today we have the pleasure of doing the non-standard. Okay, so let's sketch now. This is a new example. The function f of x equals, I think we're just going to go right into the fire here, okay? We're not even going to mess around. We're not going to take baby steps, I guess. There we go. There it is. So what we want to do here is we want to try and sketch this, right? And I'm going to put here next to this, it's in non-standard form. And as a reminder, non-standard form from last class meant we had ax squared plus bx plus c, right? That was what non-standard meant. So we could look at this right now. If we wanted to, we could identify a, b, and c, couldn't we? A would be 2, b would be -8, and c would be -1, okay? So with the non-standard form, there's no switching. Like when the h and k, we had to switch the switch. With the non-standard form, a is whatever a is, b is whatever b is, c is whatever c is. All right, same set of steps. First step, does it open up or down? Okay, opens up because what's positive? Because a is 2 in this problem, and that's positive. So that means that our parabola will open up, which means our vertex will be the lowest point on the graph. Is that okay? Most people get that on the test without fail. The next thing is the vertex. Now the vertex, when it's given to you in standard form, like we did last class and just now, the vertex is right there. Now it's not right there. You don't have h and k just looking at you. You have to use the formula. Okay? So I gave you the formula last time. I said that the h will always be -b over 2a. And I told you that k will always be f of h. That's the formula. On your cheat sheet, you should have those. So let's do h first. For us in this problem, what is -b? +8. -b means the opposite of b, doesn't it? But our b is -8, so we're doing a double negative, which makes it positive. So we have +8 divided by 2 times a, but a in our problem is 2, so that's 8 divided by 4, which is 2. And I made that very nice for you, so it came out to be a nice integer. They won't always come out to be nice integers. Next example, I'll make it real ugly. All right, so you'll get fractions and all sorts of stuff. You're welcome. You're welcome. Always keeping you in mind over here. Hmm? How'd your anatomy go? Should I ask? Okay. This is your your class. Sorry about that. Yeah, I should have been specific there. All right, so we take that answer to get k, we take that answer and we plug it into our function. So I'm going to take 2 and plug it into the function. So let's plug it in. That means I have 2 times 2 squared minus 8 times 2. Oh, I have no idea why I put negative 2. Well, I do have an idea. It's probably because I didn't have any sleep last night. But so 2 times 2 squared minus 8 times 2 minus 1. So just evaluating the function at 2. Right? Order of operations, 2 squared first would be 4 times 2. That gives me 8. Negative 8 times 2 is negative 16, and then take away 1. So negative 9. Questions there? So we had to do some work for vertex, didn't we? And every time we have to do some work, there's always room for error, right? You have that room for, oh, you miss a sign. So I'm going to write it down underneath vertex over here. I'm just going to actually put 2, negative 9. That's my vertex. That's the point that I'll graph. And now I'm going to move on to step 3, which would be to do a quick sketch. So 2, negative 9, 1, 2, down 9, somewhere down there, and it opens up again, and so I have x-intercepts. And I have 2. On your homework, you had a problem that only had 1 x-intercept, right? All right, what now? I have 2 x-intercepts, right? So how do you find x-intercepts? Set the function to 0. So I take my function, which was 2x squared minus 8x minus 1. I set it equal to 0. Now, before, right, the problem we did before this and last class, I said when you have the standard form, you always move the number over, you divide through, you do square root on both sides, right? That's the way. When you're in non-standard form like this, you do not do that. You look at this quadratic equation and you either factor it or use a quadratic formula. So I know a lot of you are real big fans of factoring, but this isn't going to factor. So since it doesn't factor, you're forced to use a quadratic formula. You have to. So in case you've forgotten the quadratic formula, I will put it over here on the side. The quadratic formula says that if you have any quadratic equation that looks like ax squared plus bx plus c equals 0, then the solutions, the things that make that equation true, the x's that make it true, will always be negative b plus or minus square root b squared minus 4ac all over 2a. Look familiar? Some things I'll point out, the common mistakes you may have forgotten. This division bar goes all the way across. You cannot divide by the 2a until after you've resolved everything in the numerator. You have to do everything on top first before you come through and divide by 2a. So I'm going to apply that formula to my problem. I'm going to identify my a, b, and c here. We already did this, but I'm going to write them down explicitly. C is negative 1. So a was 2, right? B is negative 8, C is negative 1. And here comes the application of the formula. My solutions should be positive 8 plus or minus the square root. Now I'm supposed to square b, right? What's b squared? 64. Okay, that number right there, I'll highlight it in the formula. That number right there, b squared, will always be positive. Okay? Regardless of what b is, once you square it, it's always positive, right? I don't know how many times I have students in the formula, they'll make that a negative 64. That b squared is never, ever negative. So don't ever put a negative there. Right? Negative 8 times negative 8 is positive 64. All right, now continue with the formula. Minus 4 times, what's A? 2 times C, which is negative 1. All of this divided by 2 times 2, which equals 8 plus or minus square root 64 plus 8 or minus 8? Plus 8, which is 72. Yeah, what I'm going to do here is I'm put a big old double, triple, whatever star here, because this is college algebra, and I expect that you could turn that blue up there into 72. If you can't, that's fine, but you need to resolve that, because that's the most common mistake on the quadratic formula, is getting the 72 from that. So make sure you understand in all the problems that we do how to get from there to there. Now, in a 0303 class or something like that, normally we would then go and try and break down 72, right? Like 9 and 8. You know what I'm saying? We don't need to anymore. Here's why. Because eventually these are x-intercepts, right? And I have to graph them. Well, if you give me an answer, something like, 2 plus or minus the square root of 3 over, something, where the hell is that on the x-axis? I need a decimal. So I'm going to go straight from here on my calculator, square root of 72. 8 plus or minus. Now, another common mistake. People will get onto their calculator. They'll do the square root of 72. They'll get an answer. And they'll keep it under the square root. Like they'll write the square root again and then whatever the answer was. But you've taken the square root, right? So there's no more square root. So I get 8 plus or minus. I'm getting 8.48. I'm going to go 8.5. Again, because this is a decimal, we have to plot it. We're not going to get any better than 0.5, How are we going to tell the difference between 0.5 and 0.4 on our graph? Now, if we were building a bridge or an aircraft, we would need to make sure that we were more precise than this, right? All over 4? Now do the top. Now, because I have to add it and subtract it, I'm going to have 2 possible answers now. So here's where I come through with my positive scenario and my negative scenario. So on the positive, I'm doing 8 plus 8.5. I'm dividing that by 4. That's 16.5 divided by 4, which is 4 point, what do you get? 1, you want to go 4.1? Is that good enough? Okay, 4.1. And then on the other one, I do 8 minus 8.5 over 4, which is negative 0.5 over 4, which is negative 0.1. Is that okay? Sorry, I know I'm way over here, but that's kind of small. But see that? Any questions? So that's quite a bit of work, isn't it, for our x-intercepts? Yeah. All right, what's next? We found our x-intercepts. What's the next thing? Well, I need to go to a new page. So for the y-intercepts, this is step 4. For the y-intercept, we just plug 0 into the function, right? And this actually turns out to be better than it is with standard form. It's really easy to plug 0 into a non-standard form function. 0 squared minus 8 times 0 minus 1. That's right. That's exactly right. That's. Are you wearing a Lakers shirt today? Okay, good. All right, all right. I just saw green and purple. Yeah. Your underwear. Your underwear. That's a little more information we needed to know. But it's good to know you're matching your underwear. Thank you for waking me up today. I appreciate it. All right. So, look, when you're in standard form, right? I'm sorry, non-standard form. This is what non-standard form looks like, right? Ax squared plus bx plus c. If you plug 0 into that, won't it always be the c? And that's what we were saying. It's just the -1 here at the end is going to be our y-intercept. So it's usually not much work to find your y-intercept. All right. Graph, right? We're ready to graph? Any questions? I'm going to go to a new page. All right. So where was my vertex? 2, -9. I should be able to fit everything on this graph. 1, 2, here's 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's -9. So there's my vertex. My x-intercepts were at -0.1. Well, here's -1, right? -0.1. Yeah, it's right next to the y-axis, right? But on the left side of the y-axis, just a little bit. So I'm just going to put, right there. If you make your dot big enough, then you can be really off with it, right? There's -0.1. And sure, I'll draw a little line from it saying -0.1. And then where's my other x-intercept? 3. There's 4. So I'll put a dot to the right of 4. And I'll say that's 4.1. So far, it's looking good, right? It's looking symmetric. Where's my y-intercept? -1 on the y-axis, which is right there. I kind of made it a blue dot. I'm going to draw my axis of symmetry just as, if you're doing it on your paper, you might want to do just a dotted line, if you even want to have it. You don't have to. It kind of helps me draw it sometimes, though. I always start at the vertex and I draw a little U down there. That helps me from drawing a V, because you're not supposed to draw a sharp corner. I'll take off points if it's a V, because the V is an absolute value function. It's not a quadratic. So I'm going to go through the left side here. I'm not going to go through the left side there. Connect the dots. Come up this way. Connect the dots. There you go. Okay, so I've pretty much covered quadratic functions. I mean, I know I've only given us one example of this with the non-standard form, but as we sit, if I give you a quadratic function in either form, you should be able to go through the process to sketch it. Yes. Yes. You have to complete the square. And I don't think it's worth the effort, honestly. If this, like I've said before, this is a terminal math class, so no one's going on to pre-cal. If you were, we'd be completing the square. All right. Now, I'd like to show you an application of quadratic functions, and then if there's any time left, we'll move on to new stuff. All right, so application. Now, when it comes to quadratic functions, there are many, many, many things in the real world that you can model with quadratics. Lots of real world situations are perfectly connected to a quadratic function. So I get to pick which one I want to show you, and I always use the same one because I think it's the most I think it's the easiest one to relate to because it's something we deal with on a daily basis, and that's gravity, right? We all have to deal with gravity, unfortunately, and fortunately, right? If there were no gravity, it'd be fun for about an hour, and then you'd realize that sucks to not have gravity anywhere, right? So, no, that's true. But if I push you, and there's no gravity, and you go out into outer space and die because you don't have oxygen, then you might be concerned. Okay, well look, so gravity affects all of us, and here I don't have any way of doing this on this little screen, so I have to get up and do this. Some of you who've had me before might, I don't remember if I've done this. The paper in the book? No? Yes, I've done the yeah. Paper in the book. All right, well, I'm doing it again. So who has a book? Anyone have a book? No, I have my calculus book right. All right, so here's what I'm going to do. If I drop the book and the paper, right, they're both obviously going to hit the ground. And the question is which one hits first and why. So I drop them. Do I really need to drop them? Yes. Yeah. Just to wake you up.
I've never seen this before.
Okay. You know what's going to happen though, right? So drop them. Book hits the ground before the paper. Now, let's do something different. Let me do this little cap in the book. Which one's going to hit the ground first?
The book because it's heavier.
Book because it's heavier?
No, I can't see.
Can't see. Good. Okay, so if I drop these together, looks like they went right about the same, right? Okay, so for a long time there was a debate. When I say a long time, I'm talking like hundreds of years ago. Okay, before we had developed mathematical principles that physics, laws of physics, and everything else. So the debate was: do objects fall to the ground at the same rate, or does their weight have a bearing on that? And it turns out that all objects on Earth fall to the ground at the same rate regardless of their weight. Okay? The only thing that stops that from happening is air, the resistance of air. So it's kind of like if I jump out of a plane and then someone else jumps out of the plane, one of us has a parachute, the other one doesn't. The person with the parachute slows down because it captures the air and that counters the force of gravity. Well, when I dropped the paper and the book, the air was slowing this down. The air had a larger effect on this than it did on this, right? And an easy way to demonstrate that and say if there was no air, they would go together, is to put the paper on top of the book. And now if I drop them, if you think the heavier one should go faster, then what should happen is the book should fall away from the paper, shouldn't it? Right. If you think it's because of weight. But if they fall together regardless of their weight, they should fall together because the book's going to move the air out of the way. And this won't have any air affecting them. So if I drop them together, they go together. Okay? So we were able to prove that a long time ago, that on Earth, all objects fall to the ground at the same rate. It was proven and people were happy. Well, some people weren't. The same people that didn't like the idea that the Earth was not the center of the universe were the same people who didn't like this. So when we got to the moon, right? When we finally got to the moon, I don't know if you've ever seen like the picture of the moon guy, and he drops a feather and a hammer. Have you ever seen that? They actually did that when they got to the moon, even though it had been proven it was true. When we got to the moon, the guy stood out there with a feather and a hammer, and dropped them, and they went whoop, together, because on the moon there's no atmosphere, there's no air. So it's kind of a up yours to all the people who were trying. It's like we already knew. It was like, hey, here, we brought the hammer and feather with us just to show you that we were right the whole time. You should have been
We
listening.
didn't bring the food and stuff.
Yeah, they ran out of gas and they never came back, but they dropped a feather and a hammer. No. So now the question became, if all things on Earth fall at the same rate, right? Regardless of whether or not it's a boulder or a rock or a pebble, right? No matter what, if all things should fall to the earth at the same rate, then that means if I drop something, no matter what it is, from a certain height, I should know how far it's gone after 1 second. I should know how far it's gone after 2 seconds. And I should know how long it takes to hit the ground, shouldn't I? No matter what it is that's falling. And so we went and tried to figure out, well, what is it? Is it maybe if I drop it after 1 second, it's gone 10 feet. And then maybe after 2 seconds, it's gone 20. And maybe after 3 seconds, 30. Does that sound right or no?
Well, I guess it depends.
If I drop something 1 second later, 10 feet, it's gone 10 feet, right? So from here, it went 10 feet. 1 second after that, would you think it would go 10 feet again?
No, because it's going to pick up speed.
It's going to pick up speed, right? Exactly. As you drop something, it gets faster and faster. So in the first second, yeah, it goes this far. But in the next second, it should go further because it's going faster than it was when I first let it go, right? It's speeding up. So it's not linear. It's not every second's 10 feet. Every second's 10 feet. It's every second something's happening and it's getting faster. Well, it turns out it's quadratic. It's exactly quadratic. So we have a quadratic function that tells us exactly what happens when you drop something on Earth. And that's going to be our application. All right? Here we go. So did we do World Trade Center? Yeah, we won't do that. We'll spare everyone the misery. It's all depressing. Okay. Oh, yeah, I know. I've left it out. I am sorry. Okay, quadratic functions. Falling objects. That's right. See, that's why I did it. Falling objects on Earth. Now, this is important. I'm going to put here no air. And I know you're going to say, well, wait a minute. Why have a formula that tells me about objects falling on Earth when there's not air? Because there is air, right? So what's the use? Well, this is the way things work in math. We start out with a formula like this that's very basic. It covers the case when there's no air. And then later on, we throw in air into the equation or into the form. And the formula becomes more complicated. And then you start getting into, okay, well, what's the density of the air? Okay, so now you have to talk about, is it cold air? Is it warm air? There's all sorts of things. It becomes more complicated, right? And as you get more complicated, these functions turn into what you get when you open up a physics book and go, holy crap, what is that? It's these functions with all these other variables thrown onto it. This is the most basic form of a falling object on Earth. This is it right here. Okay? Also, I'll point out this only works on Earth. So if you happen to be on a different planet, this will not work for you, okay? But there is a way to get the equation on different planets, okay? It all depends on the acceleration of gravity. So let me put the formula up and then we'll explain what everything means. D of t, so I'm using d of t instead of f of x, okay? D of t equals negative 16 t squared plus v with a little 0 under it, t, plus d with a little 0 under it. That's it. This is it. Now let me explain what all these little things mean. First of all, in the problem, t is time. And in the formula, it's always measured in seconds. In the formula, d of t is the height of the object after t seconds. Now, I really want you to understand what that means. Remember when we talked about functions, there was always input, output, right? Input, output. This function, the way it works is this. You give it a time, it tells you how high the object is, okay? That makes sense? The input is how much time has gone by since you dropped it or let it go. Okay, so you always have a starting. Like I'm sitting here, I'm holding my calculator, I'm about to drop it. Ready? I'm not going to do it. And then I start the clock as soon as I let go, right? Okay, so the output of the function is how high off the ground it is. Now, does it make sense? Well, hold on, I got ahead of myself there. Let's look at the other things. This little v with the 0 here. The way you say that is v naught. V naught. And what it is your starting speed. I'll explain this in a second. It's your starting speed. It's measured in feet per second. I forgot to put what units the height's in. In this formula, the height, like when it spits out the answer, the height it gives you is always in feet. Okay, it's not in miles or anything like that. Inches, it's always feet. Okay, so you put in how much time's gone by in seconds, 2 seconds, it spits out how many feet off the ground it is or how high it is off the ground in feet. The starting speed is given in feet per second. Now, this is a little tricky, but I don't want to make it so tricky that you're like, what? If up v naught is positive, if down v naught is negative. Okay, so I need to explain this by getting up and showing you what I'm talking about. I've always wanted to teach this class. I think that's where I would love to wind up in physics. I love physics. But
What's the problem? Keep going.
the college didn't, the physics classes never made. So I would have never graduated. You know what I'm saying? But, all right, so if I drop this marker right there, that's just letting it go. There, I'm looking at V naught, said starting speed. If I'm just holding something and I let it go, it doesn't have a starting speed. It's starting at 0, right? I'm just letting it go. As opposed to, I'm going to let this one go and I'm going to give this one a starting speed, okay? All right, now I gave that one starting speed, it got there faster, right? So if you have an object and you give it a starting speed downward, okay, downward, then you will put a negative number here, okay? A negative right in front of that t. With me? If you give it an upward speed, you put it as a positive. So I'm going to let this one go. I'm going to give this one upward speed. Okay? So I turn my hand. So that one goes up first, then comes back down, right? So that's what that starting speed is. It's if you're giving it anything initially before you as you let it go, you throw it up or throw it down. Got it? The last thing in the formula would be the D naught. The D naught is your starting height. And it's measured in feet. That's it. That's everything we need. So, time for a problem? Ready? A helicopter Copter, is that right? A helicopter is ascending vertically at a speed of 0.75 feet per second. At the moment, it is 200 feet off the ground. It drops a bomb. We're going to blow something up with this helicopter, all right? What's wrong? Yeah, it can happen. Yeah. I needed something that could go straight up. So, all right. So, what's happening here is we have a helicopter, right? It's ascending, which means it's going which way? That's descend. Ascend. Yeah, ascending means it's going up, right? So it's going up at a speed of 0.75 feet per second. So that's under a foot a second. That's not very fast, right? It's going up. And when it gets to the point where it's 200 feet off the ground, it drops a bomb. The question is going to eventually be, how long does it take for the bomb to hit the ground, right? But I have a couple of other questions for you. First thing, how high does the bomb go? In other words, what is its highest point? And then part B, how long until ka-boom? Is that the way you spell kaboom? Okay. More O's. That means how long till the bomb hits the ground, right? Now, a lot of people will misinterpret the first question, and they'll just say 200 feet. Is that the highest the bomb ever went? You let it go at 200, so what do you think? Is that the highest point? It's yes or no. So do y'all want to vote? How many of you think 200 feet is the highest the bomb would go if you let it go at 200 feet? Only a couple people want to be honest. All right. And then how many people think that it's higher than 200 feet? Or lower? Okay. Well, let me give you an example. Here's my hand. If I just let this, let's say this is 200 feet right here. Okay. If I let this go, what's the highest the pen was ever? I mean, that's not good English. How do I say that? If this is 200 feet and I just let it go, then what was the highest the pin ever was? Right? 200, right?
Yeah, but the helicopter's still going up.
But the helicopter's going up. So watch. Now my hand's going to come up. Now I'm going to exaggerate this because 0.75 feet per second isn't very fast. But I'd like for you to watch what happens to the pin. I'm going to let it go. Let me see. I'm going to draw a line here. That's not very straight. I'm going to let it go when my hand gets to that line. I want you to watch what happens to the pin. You see what happened? Because it had a speed going up, right? And even though I let it go, as soon as I let it go, it still had speed. So it had to let gravity say, and come back, right? That's what had to happen. So, anyways, even though we let it go at 200 feet, it still came up a little bit and then started dropping. So we want to know how high it went. And then eventually we want to know how long it took to hit the ground. But this is a quadratic function, right? So what do you think the highest point of the bomb corresponds to? It's a quadratic function. Go back to what everything falling on Earth looks like. That is a quadratic function, isn't it? Our variable here is t squared, t, right? So isn't this like ax squared plus bx plus c? Okay. What is a for us? Negative 16, which means that this parabola opens which way? Down, which means it has a highest point, right? That highest point corresponds to the highest point of our bomb. Make sense? Okay, so I'm going to go back to where we are here. Let's identify some things from our word problem here. Working on the solution down here. Yes?
In letter A, is the answer going to be the same for both questions? How high is it going to go and what is its highest point?
Yes, that's the same. Yeah, that should have been, in other words, what is its highest point? Yep. Let's see here. D of t is negative 16 t squared plus v naught t plus d naught. Has anybody taken a physics class before? Anyone? Okay, do you remember in physics them telling you the acceleration of gravity is 9.8 meters per second per second? Do you remember that? Or negative 9.8? So you rounded to 10? Okay. Do you know how many feet are in a meter? About. How many feet in a meter? This is almost a meter stick, right? It's about 3 feet, right? It's about 3 feet? Okay. If you take, it's actually a little less. If you convert 9.8 meters per second over to feet, convert it from meters to feet, you get 16. That negative 16 out there is actually the gravity. And so if you were on the moon, the negative 16 would be cut by a third because the gravity on the moon is about a third less than here. I mean, it's a third of what it is here. Anyway, I'm just pointing out to you that negative 16 is always the same in every problem you ever do with falling objects on Earth because it's gravity, basically. All right, well, let's get to the rest of this. Let's plug stuff in. What we have in this problem is negative 16 t squared. Do we have an initial velocity? Was the bomb moving when we let it go? Well, the helicopter let it go, right? It was. It was moving 0.75 feet per second. Up or down? Up. So I'm going to put a positive 0.75 t, right? Plus d naught D naught is the starting height in feet. So where did I let the thing go from when it started? 200 feet. Right? That's it. Okay. Here's what I'm going to do. I'm not going to continue the problem. You have a quadratic function here, right? That is in non-standard form, and it has decimals. That's your homework problem. Now, not to answer this question, what I want you to do for homework is I want you to sketch this. Forget that there's even a bomb being dropped anymore. Just take that function and sketch it. Act like it was f of x equals negative 16x squared plus 0.75x plus 200. That means go through the 5-step process. 1, does it open up or down? 2, what's the vertex? Well, you'll have to use the formula for it. Yes.
I'm going back to last year.
Mhm.
You didn't have a full graph, right? You just had.
But I want you to not even think about the word problem right now. When we come back, we will put it all together. Okay? But this is going to be a take home. I want this to be, I said homework. This is going to be a quiz. I mean, I want you to do it. I want you to be able to turn it in. Because when I start class next time, I'm going to continue this and answer these questions and talk about domain restrictions and everything else. So we have to first get this graph. Now, in addition to that, as a quiz, separately, you should try these for homework. Sketch the following. F of x equals negative x squared plus 4x plus 5. There's one problem. Let's see if I can mix you up at all here. 3x squared plus 12x. I want to see how you do with that because I didn't put a C on it. So, what are you going to do? It's, are you going to make it harder than it actually is? This is actually a little easier to do than the ones before. And we'll do one more. The last one will be the hardest one. 2x squared minus 5x plus 4. Now let me give you a hint on number 3. Not a hint, but just some advice. Because it's in non-standard form, you have to calculate h and k. For vertex, h is negative b over 2a. When you take negative b over 2a here, right, h is negative b over 2a, you're going to get positive 5 over 2 times 2, which is 5 over 4, right? Make it a decimal. Before you go plug it in, because now you have to get k, which means you have to plug it in the function, make it a decimal. Use your calculator to figure out k. All right? So this is 1.25. So please do that homework and absolutely do that quiz problem. I haven't taken attendance lately, and I'm letting y'all go 10 minutes early, so just hold on. I want to take attendance. Oh.